Hello to any and everyone watching, or who is catching this later in the archives. My name is Joshua Phillips. This is Math with Josh, the live streaming. You're going to hear a little bit of echo here. It'll load. Hello to any and everyone. Okay. Pause that. Again, my name is Joshua Phillips for Math with Josh. This is a mathematics channel. I have it listed in science and technology. We're going to be doing some live math homework help, so you can submit your questions or puzzles you ran into that you found interesting, and I'll try to work on them. You'll see some contact information down at the bottom of the screen, so message me wherever that works on that page, and I'll try and incorporate those into the show as pre-prepared stuff. If you catch live, I'll try to do them live on that episode. If you're interested in supporting the channel financially, I don't have that quite set up yet. I'm trying to get a PayPal account set up. I got a little bit rushed today. Might have a Patreon set up, etc. I know Twitch has a subscription feature, so that's interesting. So might have that at some point in the future. For today's episode, I'm not quite sure how long this is going to run. I'm going to talk a little bit more about the channel and the ideas here at the beginning, and then I'm going to sketch. I think I've shown this previously before over at the YouTube page, but I'm going to sketch. I'm not going to call it a proof, but an intuitive explanation for where certain calculus properties of derivatives come from. It leaves you a little bit open-ended to think about when that intuition might break down, how that intuition would interact with, for instance, negative numbers, which is important. To talk about some of those properties, show this intuition for where the product, quotient, and chain rules come from. Okay. And of course, if you have any questions, you feel free to just ask them in the chat. I am looking at the chat intermittently. I'm going to jump into the pre-prepared lecture type thing I had ready for today. So again, this is, you can think about this as, see if I get the box to pop up. Some intuition behind the product, quotient, and chain. Let's make sure the words are in the middle of the screen. Chain rules for derivatives. Now, obviously, because this is a calculus topic, this is fairly advanced. So, as is often going to happen, I know this won't be accessible to absolutely everybody. But if you're a high school student in calculus, or if you want to remember to save this for when you get to calculus, I think this explanation really helps in terms of seeing where these rules comes from in a physical sense, not just the theoretical proof that they work. And of course, the theoretical proof is a proof, and this is not quite a proof. But I think for a lot of people it helps, and if you ever forget these derivative rules, then you can not quite prove them, but you can go back through this intuitive argument I'm about to make to find them again, realizing you haven't quite verified them. So I'm going to clear the screen off here. Let's see. Now the properties we're going to talk about today for the lecture part are, if I can get my brush size correct, the product rule, that f times g, the derivative thereof, or fg prime, is equal to f prime times g plus f times g prime. And I would like to note here, I think there are a few different ways this is ordered. I've seen people show it as f prime g plus g prime f. That's fine. I'm going to show it this way. Certainly the algebraically equivalent and correct ways are also fine. I just like putting the letters in the same order. So the product rule, the quotient rule, which is that f over g, the derivative of that, which is f over g prime, is low d high minus high d low over the square of what's below. Is that a limerick? Do I remember it via the limerick? Yes. Yes, I don't remember it via a rational proof offhand. Remember, it's low d high minus high d low over the square of what's below. Spoiler alert, the quotient rule is really just a special case of the product rule. And the chain rule, which is that f of g of x, which we can also just call f of g for the sake of this, how was I showing this? The derivative of f of g, or f of g prime, is equal to f prime of g times g prime. That is the derivative of f with g as in place of the variable times the derivative of g. Let's move this off to the side a little bit for what we're going to cover. And so again, these are all intuitive explanations. They are not proofs. So for the product rule, we want an explanation of why again, remember, derivatives are rate of change. We want an explanation that is intuitive and physical for why the derivative of a function that can be seen as a product ends up having a nice convenient rule, which is f prime times g plus f times g prime. By the way, just really quick, a context for why you might want a rule for this. Imagine we had the function x squared sine of x. Well, we can't multiply those two functions together, so we need the product rule if we want a derivative for this function. Right? There's no nice way to congeal x squared and sine of x at this level. I'm not quite sure how the series expansion might handle it, but whereas if we imagine, the product rule, the point is not mainly, if we imagine some situation like x squared times x plus 1. Now, maybe, x squared plus 1, not my best lettering work there. In general, we'd realize that we can actually distribute this and get x cubed plus x, and we can just get the derivative from there, would be 3x squared plus 1. Now, the way I like to show the explanation for where this comes from is, well, f times g, that's a product, that's one thing times another thing. And the most most basic practical application of products we have is to area. So let us imagine this badly drawn rectangle. And we'll say the height of this rectangle is given by f, and the width of this rectangle is given by g. So the area of the rectangle is f times g. Well, imagine that both f and g are changing. And here's the first little step where this isn't quite a proof. I believe it extends very naturally, but we're skipping a little bit here. Let's pretend, just for the sake of this intuition, that f and g are both increasing. By the way, it's both for the understanding and simplicity. Also the fact that I'm not sure how good me trying to draw negative space would be. So let's switch to a red color here. And we want to know how f times g is changing, because we have this instantaneous increase in f and g. That they're both getting bigger. Right, so the width of this little section is how much G is changing instantaneously. That's a triangle for delta G. This change in the height is delta F. And we think about it as this change is very, very small, right? As the instantaneous change is that we'll have three little strips that are the change here, which is this rectangle on the right, whose area is F times delta G, which is the change in G, plus this top rectangle, which is G times, and I'm drawing it backwards here to fit my formula, times the change in F. And again, I'm skipping a lot of stuff for the sake of this being intuitively clear, that when we think about the instantaneous rate of change, oh, I'm sorry, this is very important. The third little rectangle here, that's delta F, delta G. Delta F, delta G. Okay. So this is our total change in area. Now the intuition here that is important is that as we imagine this change, instead of being a big change, being the instantaneous change, that is the area that would be added in a moment. Well, that's equivalent to the derivatives, so we can rewrite those. Think about it this way, that so we'd have f prime, let me go back to a slightly different color. We would have f g prime plus f prime g. And the important thing that justifies the product rule here is as we go to an instantaneous rate, this being two deltas will make it insignificant. So we can round it off to 0. And if you want to think about why that's possible, we can compare. So the area of the little corner up here is delta F times delta G. We imagine those deltas becoming infinitesimally small. Well, the ratio of the size of the top right corner, that's two deltas. It's an infinitesimal ratio compared to the two long side panels because they only have a single delta in them. Or if we think about it in practice, right, imagine delta G, imagine the two deltas here are, about 1/millionth. Well, that would be, 1/millionth of F and 1/millionth of G for these two side panels. But the corner panel would be a millionth of a millionth. And of course we go to a billionth, but it would be an extremely small fraction of the extremely small fraction, and thus negligible. As you make those numbers smaller and smaller, it becomes more and more insignificant. So that is, I think, a very useful intuition about where the product rule came from, that we look at the change in a rectangle instantaneously. Now, if you're watching this, you might realize that, what if delta F is negative? What if delta G is negative? What if the functions F and G are already negative? These are all very good questions. And you can check them. I believe they all work out just with the same concept. You have to figure out how to draw the idea of negative space. But that's the basic intuition. Let's see if we can get this erased. Now, the quotient rule, which is the rule... let's do the chain rule first so that the quotient rule, we can skip some steps. So the chain rule is the rule that if we have f of g, the derivative of that is f prime with respect to g times g prime. Now, the way I think of this is that in this one is a little more abstract. Let's imagine we have a function f, which that was not a straight line at all. Let's imagine our function f describes how long a straight line is. Excuse me. That is how many blocks the straight line is made up of. And this is the slightly weird part. Our function g determines how big each block is. Let me repeat that, because otherwise this gets very weird. F describes the number of blocks in, the number of sticks in the fence, and G describes the length of the individual sticks. Well, if we want to know, let us imagine we would be asking in this context, what is the rate of change of the fence length? Well, the fence length, as it is of course the number it's the number of fence posts times the size of each fence post. That's the size of the fence. But we have to back up and remember that f is actually determined by g. So f of g is how this gets hashed out. So let's think about how the fence changes from one moment to the next. And for this, we have to imagine the change to a new fence. Well, here, and again, I'm skipping a lot of steps because it's the intuition behind calculus, not the actual calculus. 7, 8. We have, put fence on the end here just to be clear. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 fence posts. And let's just say, so 9 links. Let's say 9 links. And let's just say each link is 3 feet long. Well, to our next fence, our fence, so let's pretend this is the end of it. We have the new fence, which is given by how much f prime of g. No, this is e. Okay. So f prime of g, which is how much is the actual function f changing. Right. F prime of g determines how many new fence posts will get put on, because this is the additional post or two that got added. And so that's where the f prime of g part comes in, right? That the number of fence posts is how that's changing over time describes how much longer the fence will get. So you might think the answer is just the derivative of f of g prime is f prime of g, that it works very naturally. But the thing we have to remember is that each fence post, and I hadn't thought ahead of time of how to draw this. That's a clear mistake on my part, everyone. I apologize. Is that let's draw our fence posts in. So 1, 2, 3, 4, 5, 6, 7. I know the numbers change a little bit. Well, each of these fence posts, we have to remember, it got a little bit longer. Right, let's imagine the pink part is the new part of each individual fence line. Because f of g of x, well, that means the number f is outputting, the number of links in the fence is changing. But also the internal part, the length of the links is changing as well. So if we think about what the change in the fence is in this context, it is actually it's actually going to be that we have our new section of fence, and that's just the change in how many fence posts this function is outputting. But we have to multiply that by the scaling that is going on to the individual posts, and that's the change in G. So that is, I hope, a decent explanation of where those two rules are coming from. The one that's a little bit easier, let me back out of a lot of this. So the quotient rule, and I think most teachers do in fact do a pretty good job of explaining this one, providing a good intuitive framework for it. The quotient rule is kind of a trick. The quotient rule is realizing that if we have some function f over g, that is equivalent to f times the function g to the negative first power. I think we're all good there. Well, so say we go to take the derivative of this. So we go to take the derivative of, where are we? We go to take the derivative of f times g of negative 1. Now, because we first looked at the product and chain rules, this will actually be fairly easy. So we have f times g to the negative 1. Well, the derivative by the product rule is going to be f prime times g to the negative 1. Notice, don't get confused, the primes and the negative 1 are different. It's hard to bold with this. It will be f prime times g to the negative first plus f times the derivative of g to the negative 1. And we'll go to the next line to simplify this, so we end up with, f prime over g plus f times, and now we have to remember our chain rule. So g to the negative first is really the function, all right, let's look at this. So g to the negative 1, we can also think about this as being the function, so if we say h equals 1 over x, oops, 8, let's not save it, okay. If you say h equals 1 over x, well, g to the negative first is really h of g. So the derivative of g to the negative first is going to be the derivative of, so first let's do the g prime part, so the derivative of g is just going to be 1. But it's going to be g prime over here. I was thinking g was a constant for a second. Sorry. So we'll just put the g prime over here. Well, the derivative of 1 over x, and hopefully you learned this, it should be in your elementary tables, is negative 1 over x squared, which in this case is g squared. So we have f prime over g plus f times negative 1 over g squared times g prime. let's go one more line down. We get f prime over g plus f g prime over g squared. I'm sorry, since this is a negative, we will actually need a minus sign in the middle here. Minus sign in the middle. And this is actually the quotient rule, right? This formula is in fact the quotient rule. But we can simplify it a little bit using the common denominator, which is to say the left fraction will get multiplied by g over g. Notice that this means there are issues if g could ever equal 0. And we get g f prime minus f g prime, and they have a common denominator of g squared, which is the quotient rule. That one I think you're more likely to have seen. It's possible that you weren't shown that the quotient rule is really secretly just the product rule applied to the situation where your product is some function f times 1 over some other function, or some function of the negative first power. Let's see, it's about 8:20 now. I don't have any questions in the chat or anything. So let's clear the blackboard here. Need a bigger eraser. So if you enjoyed that, I'd absolutely love any constructive criticism on my presentation. I think I'm learning from doing some of these shows. I need to be better prepared. I need to have notes written down beside me and not just try to remember calculus formulas from memory. That has certainly had some limitations. I think some of you might have noticed them tonight and how rigorous my explanation was. But I think that intuition that we went over for at least the product rule, which I think is easier to understand, less weird. I know weird is not a formal term, but less weird. That often the product rule is taught and stated as true, and you aren't shown the intuition. I keep using the word intuition, I'm sorry. It annoys me when people use the same word a million times. That there are good explanations that are not necessarily proofs of where certain important mathematical ideas come from that I think are worth looking at if you want to have a better understanding of the math. Most famously, and I showed this one last week too, right? A lot of people don't realize that FOIL multiplication for polynomials, and I'll leave it to anyone watching this week to figure it out. So if we have some a plus b times c plus d, we have this FOIL formula for how to multiply those together. So if we had, imagine x plus 2 times x minus 3, and we wanted to multiply those together, there's a formula called FOIL, and it works, it's correct. But often people don't get an explanation for where it comes from. And the figure I've drawn here on the screen, if you've made it through the calculus talk, I think you can see from here and imagine for yourself, what is the area of this figure? And as I say whenever I show this, part of the advantage is when you look at it this way, if we imagine adding some more letters, it actually becomes clear what the general idea of how to multiply polynomials together is. Whereas if you just learn FOIL, this could actually be quite the problem, because if you were taught FOIL and you were taught that's how we multiply polynomials, that's how it works, and then you end up with some problem like this. Let me put my parentheses in. Times how did I do that? I just drew a delta somehow. That was weird. What just happened? Wow. Well, if you were just taught FOIL, you can't do that because you weren't given the general idea that would come up. And of course, the underlying idea is that you take each part of the first term, you multiply it, you distribute it through the second terms, you write all those answers, those results down, then you distribute the second number, then you distribute the third number, and you sum those up. But I prefer to teach and explain things in a way that allows for you to realize the general idea moving forward. So let's see. One more look at this. I think this technology works. I'm testing out some stream marker technology to do certain things too. So now I'm going to put in puzzle and see if I can insert a neat little puzzle, like after this point, see if the tagging works. So that if you're watching this video in the archives on YouTube, for instance, or on Twitch, you can just click ahead to the puzzle if you're just here for the math puzzle. So today's puzzle, let's put a little tag in. Let's jump over here. What's a good puzzle for today? Let's see. I think I've done that one. Oh, well, this is not so much a puzzle as a simple math problem. But let's say we have a standard deck of cards. So, suppose we have a standard deck of cards. And this will test whether you've figured out some basic probability ideas. Sorry, it's kind of disappointing as a puzzle. We shuffle the deck to be randomized. Then deal 5 cards off the top of the deck. What are the odds we deal, in the order I'm about to give you, an ace, then a king, then a queen, then a jack, then a 10, all of which are the same suit. So to think about this, if you want to visualize, we have a deck of poker cards. We're supposing it's been shuffled to be perfectly randomized. We then flip 5 cards off the top of the deck. We go 1, 2, 3, 4, 5. What are the odds that the first card is an ace, the second card is a king, the third card is a queen, the fourth card is a jack, and the fifth card is a 10, and all of those cards are the same suit? I like this problem. Be careful. There's a subtle little wrinkle in the way it's worded. It's important to catch that. And if you haven't seen something like this before, it might introduce you to some basic important ideas in probability. Okay, so we had a little puzzle. I'm actually going to call that for the night, everybody. I know I said 8 to 9. I apologize. I got a lot busier than I thought I was going to be earlier. And I do have some things to do before 9 o'clock. So thank you to everyone who tuned in, however briefly. If you're catching this in the archive, thank you very much for watching. Once again, my name is Joshua Phillips for Math with Josh. You can see my contact information down at the bottom of the screen. Thank you. Send me your questions, and have a good night.